so that I could really see everybody and we could have discussions. But this is good. This is a good thing. And yeah, I mean, I'm Dr. Katherine Romanak. I've been working in carbon capture and storage for almost 20 years now. Before that, I actually got my PhD 2 weeks before the birth of my second son. It took me quite a long time to get my PhD, and I was a mom for 10 years. I decided I just wanted to be with my kids, and so for 10 years, I raised my kids. And then one night, my husband said, "Why don't you get back into geology? It's your passion." And so I made a couple of phone calls, and I found out there was this thing called carbon capture and storage that was being developed, and they needed somebody with my expertise as an environmental geochemist to help to see if this technology was something that could work, and just to really start researching it and developing it. And it was interesting. The first job I had, so I landed my dream job at the Bureau of Economic Geology, and the first task I had was to look at the geochemistry of the drinking water above the Sack Rock oil field, because that is the longest running CO2 injection in the world. It's been injecting CO2 nonstop for enhanced oil recovery since 1972. And they said, "Katherine, you're an aqueous geochemist. We want you to go and look at this groundwater and tell us, has any of that CO2 made it up into that groundwater?" And so that was my first task. And I actually found out that it had not. There was no evidence at all that any of that CO2 had made it into the aquifer. But that's what began my 20-year kind of after mom type career, just really looking into the environmental impacts and really what happens to this stuff when you put it underground, and can it work, and is it going to be safe? And so that's what I'm going to talk to you about tonight. I know that there's a lot of different opinions on carbon capture and storage, so that's cool. I just want to kind of tell it to you tell you what I know from my 20 years of research. So I'm going to go ahead and share my screen, and I have a little presentation. So share my screen. And can you, well, you're going to have to tell me if you have the right view of it.
There it is.
Now, do you see it? Okay, great. All right, so again, I'm going to talk to you about carbon capture and storage today. And what I want to do is just first kind of a scene setting, and then talk to you about what it is. There's a lot of misunderstanding and misinformation going on around this technology. And so I just want to nuts and bolts, this is what it is. And then talk about some of the aspects that I've been hearing people concerned about and discussing, really safety, cost, and the viability of the technology. Does it work? Can it work? And then I'm just going to end with a couple of analogs, and then hopefully we can have a chance for discussion, because as I said, if we were in the room together, we might have more of a dialogue. But I think it's really important. I just got back from COP28 in Dubai, where an unprecedented agreement was made. I'm going to talk a little bit about that, but what I want to say is I think the only reason why an agreement could be made under these contentious, environment is because we were utilizing the dialogue used by the ancient indigenous cultures in Saudi Arabia called the Majlis. And the Majlis is really about, hearing people and having that dialogue and that discussion. And I think we need more of that in this country just overall. And so I'm really grateful for the opportunity to do that. So I'm with the University of Texas at Austin in the Department of Geosciences, and there are 3 arms to the Department of Geosciences at UT. And I happen to be in the Bureau of Economic Geology, which is the State Geological Survey. So I work basically for the State Geological Survey. And our mission is to serve society by conducting objective, impactful, and integrated geoscience research on relevant energy, environmental, and economic issues, and to inform people about geoscience issues. And so again, I want to thank you for giving me the opportunity to do that tonight with you. So within the Bureau of Economic Geology, I am part of the Gulf Coast Carbon Center. For the past 20 years, we have been researching and developing mostly the storage aspect to carbon capture and storage. We're a large interdisciplinary international group with international research fellows, a cast of scientists, and then we also have postdocs and students. And we work with emitters, we work with policymakers, and we also work with NGOs. So we work with any stakeholder that wants to learn about or do carbon capture and storage. So that's what we do. Now, I am just being overloaded by the misinformed opinion that I am seeing all across the board on climate change. It just seems like somebody's got a disagreement about a technology, or they're going to bash this technology or that technology. And there's really a lot of energy being put into the space. And so as a citizen that cares, how does somebody say, wade through all this? How do you know what's right and what's not? How do you know what to believe and what not to believe? And what I like to say is that I think what we first do is start with what we agree on. Okay, we need climate action now. And we are in a climate emergency. I mean, this is happening, just the conversation we were having before we started this. I think you all know very well that this is serious stuff, and we need to act, and we need to act now, and we need to act big. So we can start with that. Now, the question is, how are we going to do that? And what's the information we use to do that? And I want to say that I think there's a really good place to go for this, and it's the United Nations Framework Convention on Climate Change, or the UNFCCC. Now, this is the main global treaty to combat climate change, and it's established in 1992, so it's been going for a while, right? And it has 197 parties, which is basically countries. And it meets every year at the COP. It's called the COP, but that's really just the Conference of the Parties, which is what it's called. It began the first COP was in Berlin in 1995, and the last one was in Dubai. And that was literally about a month ago, and I was there, and I'm just back from there. And what I will tell you is that a lot of people are really frustrated by this framework. They say nothing happens, nobody gets anything done, it's just a sham. But let me just tell you that the people, I've been going to this now for the past 10 years. The people work very hard at this conference, and they care. And the reason why it's so hard to get anything done is because it works on consensus. So every single country has to agree to anything that's agreed in this forum. And if you think about it, getting 197 people to agree on something would be difficult. Consider 197 countries, right? So it's a very rigorous protocol, and it's very difficult. Only one country has to say we don't agree, and the whole thing's shot. So it's an important environment. It was the environment that had the Kyoto Protocol, and now, of course, we have the Paris Agreement, and everything that is done there is heavily informed by science. It has to be. And it is heavily informed by the Intergovernmental Panel on Climate Change, the IPCC, and the International Energy Agency. And the rigorous, this is another thing I think a lot of people don't understand. So you've been talking about, and I love that you all are so informed on this because you care. The special report on 1.5 that came out in 2018 was a IPCC report. Now, these things are so rigorous. 91 scientists from 40 countries wrote that document. And it can, as I said, it can only be based on peer-reviewed scientific literature. And there are 6,000 of those references in the 1.5 report. And what the 1.5 report said was that we need deep emissions reductions, and we need rapid, far-reaching, unprecedented changes in all aspects of society. And because we're not making our targets, we're going to need removal. We're going to have to take CO2 out of the atmosphere at some point. The sixth assessment report comes with several working groups that just came out in 2022 and 2023. And these documents were written by 234 scientists from 66 countries, 14,000 scientific references. And the summary for policymakers had to be approved line by 195 governments. Okay, so now you really see, hopefully, just how difficult it is to get anything through this forum. The sixth assessment report says we've got to cut emissions now. I mean, we have this decade to make a difference. Otherwise, we're in even worse trouble. We have to scale up resilience because already we're going to have climate change impacts. We can't get away from that. And we need to cut, isn't this interesting? We need to cut global greenhouse gas emissions by nearly half by 2030. Oops. This is serious. We are not making our targets, and we're nowhere near making our targets, all right? So we need action, and we need it along every single dimension that we can. So I think you already know this, but if you look at that inner circle, you'll see that the global sources of greenhouse gas emissions are prevalently from energy production. 75% almost is from energy production, but we also have greenhouse gas emissions coming from industry like cement and iron and steel. We have waste, such as coming from landfills. And then we have emissions from agriculture and forestry in deforestation and agricultural and livestock practices. So it will be of no surprise to you to see that most of the mitigation strategies that are called on to reduce emissions are around energy. We need, and these are the ones that are accepted by the IPCC, okay? We need efficiency and conservation. We need wind, solar, geothermal power, biomass fuels. We need nuclear. We need fuel switching, for example, from coal to gas, because gas has less emissions when you burn it. We need terrestrial sinks, and we need carbon capture and storage. Now, there's a new one coming on that I talked about, I alluded to, and that's removals. Because we are not making our targets, we are going to have to also start taking CO2 out of the atmosphere. So what is the role of carbon capture and storage in this portfolio of mitigation options? Well, I'm sure you all have seen the wedge, but it's a really important concept, so let's kind of talk about it. So this is the billions of tons of CO2, the gigatons, billions of tons being emitted, and then this is time. And as you see, our emissions are going up and up and up and up and up. And if we don't do something about it, then they're just going to keep going up, all right? But we need them to go down like this. And so what this is telling us is the percentage of these mitigation strategies that we're going to need to use to get to this lower line. Now, the other thing about the wedge is it's a wedge, which means that what we're aiming to do is start small at first and then upscale and ramp up over time, all right? We see here that efficiency is going to have to be close to, well, like a third. Renewables are going to have to be at least a third. Fuel switching for 8%, 3% nuclear, and then 9% CCS, and 12% other. And I'm going to be honest with you, I'm not real clear on what other is, but the message here is that this is for energy, right? So these are the percentages of all of these mitigation activities that we need to do for energy. But the full role of CCS is going to be even more, because as I'm going to argue and discuss today, one of the roles of CCS is to stop emissions from fossil fuels while we transition away to renewables and to provide dispatchable power to support renewables when they are not fully functioning. There's a lot around production of hydrogen. And we also know that we are going to need CCS to decarbonize cement, steel, and other maybe petrochemicals or other industrial processes that actually, even if you use renewables to power those, you still get emissions because they are inherent in the process. To make cement, you have to give off CO2. So we're going to need it for that. And then it's also going to form the basis for large-scale removals like bioenergy with CCS. If the trees and the plants take CO2 out of the atmosphere, you burn them and capture the CO2. That's considered a removal. Or direct air capture with CCS, which is literally taking CO2 directly out of the atmosphere by moving it through fans and capturing that. And I will talk more about that as well. So the full role of CCS is actually more like about 12 to 13% of the global emissions. Okay, but again, we are losing the battle and we're losing it hugely. Here's that same wedge diagram again. And here's what you see, this red triangle are all the pledges, all the plans, and all the promises that countries are making in how they're going to reduce their emissions. And if you look at these, you'll see that it only takes us to about 3% warming. So we are nowhere near where we need to be. So we need a full frontal assault on this. We need to do everything. And this is the point I'm trying to make here, is that if a technology is included in the UNFCCC, then it is an accepted technology and it needs ramping up. So we need to be supporting all of these technologies being ramped up. But let's talk more about that. Okay, so where are we now? Well, in the 20 years that we've been doing CCS, we've stored not yet a gigaton, okay? And we are currently storing a little more than 0.04 gigatons a year using CCS. But we need, for that little wedge, we need 4 gigatons per year by 2035. And we're going to need to store a total of 220 gigatons by 2070. Just, we need to store it. And 56% of that's going to be from power generation, 31% from industry, and 14% from removals, okay? But I hear a lot of people saying CCS is a unicorn technology, it doesn't exist, it isn't anything, it's not a thing, so we shouldn't be using it. But I want you to know that it is a technology that is accepted within the United Nations Framework Convention on Climate Change, and I want to talk to you a little bit about the history of that. In 2001, at COP7, they actually invited the IPCC. They said, could you please write a technical report on CCS? And in true IPCC fashion, it was written by, hundreds of authors, hundreds of reviewers using peer-reviewed literature. And in 2005, the final report was approved. And this report is available to anyone online. You can get it very easily if you want to learn more about CCS from that. But then in 2006, it was included in the accounting protocols. So the IPCC has guidelines for how do we do inventories on how much we're emitting, how much we're not emitting, like how do we keep an account of our emissions? And so there's actually a chapter in the IPCC greenhouse gas guidelines, chapter 5, on carbon dioxide transport, injection, and storage. So not only is it accepted within the UN with the IPCC report, but it was also given guidelines for accounting the mitigation by CCS. But then there were these negotiations that went on in the COP, because the next step was to bring this technology into the Clean Development Mechanism. Now, the Clean Development Mechanism is a mechanism that actually helps developing countries mitigate and adapt, and gives them money to do so, right? Because big emitting rich countries need to be paying for developing countries to adapt and to mitigate, because they're not the reason for the problem, right? So this clean development mechanism is for that purpose, to help that happen and to make funds available. So for 5 years at the COPs, this was a huge discussion, and nobody could decide, should we let it in? Should we not let it in? Because there were questions. There were questions that countries had on the viability of the technology, the safety of the technology, and the long-term liability of the technology. And so for 5 years, they went back and forth, back and forth. And then in 2010, the host was Cancun, was Mexico. And they said, all right, this is it. We're going to may have a decision next year in Durban, and it's either going to be in or it's out, but we're not talking about it anymore. So these policymakers, they said, okay, but we need like a place where we can get our questions answered. Because in a COP environment, they've got to really toe the line of the country, and it's not an open forum as much as it could be. So the organizers got a workshop in Abu Dhabi where they brought in scientists to talk about these issues, right? And to answer the questions. And so then in 2011 at COP17, it went for a vote and it was allowed. And so what you know about that is if CCS was allowed in, then every single country had to say yes, and they did, okay? So it is a bona fide mitigation technology within the United Nations Framework Convention on Climate Change. And so for the past 10 years, myself and my partners have been doing side events, going into the COPs, and just making, scientific information available to policymakers and anybody else through side events and meetings and such. Okay, so what I want to tell you there is that CCS has been rigorously assessed and accepted by all the countries. So in order to have that agreement about the CDM, they needed to have regulations and guidelines for the safe storage of CO2, okay? And global regulations and guidances are in place. And these are in place to demonstrate that the CO2 remains stored. You have to make sure that it stays down there. You have to ensure that it's not impacting drinking water or the biosphere, or if you go beneath the seabed, it can't be impacting the marine environment. And then you have to be able to account for emissions reductions or the loss of emissions reductions if there's leakage. And so here's just a sampling of some of the early guidelines and regulations for those very things. And you can see that there's many and there's several. And so we have that, like that's in place. We have the regulations for how to do this. So what is it? So again, it's any stationary industrial facility with a flue stack. Any industrial facility that emits CO2 out of its flue stack, the capture can be put on that flue stack, okay? It can be gas, biomass, coal, cement, it doesn't matter. It's captured, it's compressed into a liquid, and then transported to a suitable geological formation for disposal and long-term storage, okay? But there's a problem with this diagram, and there's a problem with most of these diagrams, and it's because they're trying to show you this technology, right, in a schematic diagram. And so the thing that's really wrong here is the scale. If I were to see diagrams like that, depicting carbon capture and geologic storage, I wouldn't feel too safe either. I mean, that makes it look like it's either in a cave or it's like 3 feet below the ground surface. So that's not a correct depiction. This is more of a correct depiction where you're actually injecting it very, very, very deep in the subsurface. It has to be more than 800 meters deep. Many of these are 3 times that, but it has to be at least 800 meters deep, which is about 2,500 feet. And in fact, as I told you, I was just in Dubai at COP28, and I found this great analogy, and it's the Burj Khalifa. It's the tallest building in the world. And here you see the Burj Khalifa as it towers above all of these other high rises, right? It's many times larger than these. The height of the Burj Khalifa is just around 800 meters. So it's just about the same as the minimum depth that we need to put CO2 under the ground. So I thought that was kind of a great way of looking at it. Put it upside down. That's how deep you have to go. Okay. So how does it really work? Okay. So as I said, the CO2 is captured from the flue stack. It's compressed into a liquid, and then it's transported and injected down into a suitable formation at least 800 meters deep. Now, a suitable formation will be one that will accept the CO2, but will have other characteristics about it that will impede it from moving upward, because it is buoyant. It is more buoyant when you put it down, it wants to move up. So what we do is we find confining systems above these injection zones, and luckily that's how geology works anyway. We have generally, when you look at a geologic stratigraphy, you'll see reservoir seal, reservoir seal, reservoir seal. So that's kind of how it goes anyway. But anyway, we look for the right place. And then when we inject the CO2 down there, it pushes the salty water out of the way. So already in the pores, okay, in between the grains of the rocks, there's brine, there's salty water, and it's taken out of the way. And like I said, it is stored in between the grains. Now, that's something a lot of people don't understand. And if I was in the room with you, I would have a rock that can take the CO2, and I'd have a rock that would impede it. And we'd put a drop of water on that sandstone, and you would watch that CO2 just suck straight into that sandstone, because there's spaces in between those grains, and that's where the CO2 goes. And the thing about that is like it likes to stay down there. It's very sticky. It's very much like if you were going to make a sandwich, and so you took some mayonnaise and you started spreading the sandwich, and then you decided that you didn't want the mayonnaise, you wanted something else, so you tried to scrape it off, and you'd see that you couldn't get it off because a bunch of it would be stuck in those holes. And so that's how CO2 storage works. There's many different trapping mechanisms, okay? The first is the structural trapping, getting the right geology. The second is the residual trapping in between those grains, where it's just stuck by electrostatic forces. And then what happens is the CO2 will then dissolve into the brine, it will become dense, and it will float down, and then it will dissolve and mineralize. So basically what happens is, over time, we get more and more storage security, because, as I said, the CO2 will eventually dissolve, it will become less buoyant, it will fall down, and then it will turn into minerals. So the storage security increases over time. So we have a workflow for this. First of all, in order to get a permit, you have to show a very high level of assurance. As I said, we have those regulations and guidances are in place. We have to do site selection and characterization to make sure the site is correct. And then we do a risk assessment with modeling to identify any potential unwanted outcomes. And then we design the project to minimize any potential risk. And then we monitor it. And it's interesting to note, we're doing more monitoring for this subsurface engineering activity than any other subsurface activity that we do. We're going to monitor in the deep zone, in the injection zone, to make sure the plume is, behaving the way we thought it would. And then we're monitoring the shallow groundwater, the soils, and the biosphere to make sure that nothing is happening to the environment. And so we're constantly monitoring this before, during, and for many, many years after the project is finished. So Is it happening? I mean, supposedly it's not happening. Where are we now? Well, these are all the places around the world where CO2 storage projects are happening. We are squarely in the upscale. We are squarely in the upscale. We have 41 facilities in operation around the world. We have 26 facilities that are being constructed, and we have 325 facilities in development. This is a year-on-year increase in CCS facilities of 102%, and this is exactly the upscale we need. We need 2 orders of magnitude upscale in carbon capture and storage, just like we need it for every other technology, okay? So that's good news. We have projects that have been running for a very long time. We have the Sleipner project, 25 million metric tons that have been stored, more than that, 1 million tons per year since 1996. Also in Norway, we have Snøhvit, 10 million tons, more than 10 million tons since 2008. We have Weyburn, which is for CO2 EOR, and we'll talk more about that. 30 million metric tons ever since the year 2000. And we have the SACROC project, more than 80 million metric tons, injection of CO2 nonstop since 1972. That's the project I mentioned at the beginning. Was my first task, was to see if that had impacted the groundwater, and I saw that it hadn't.
Hey, Catherine, where is SACROC? Where is SACROC?
SACROC is in Scurry County, Texas, so it's just off the Caprock near what's the name of the town? Sorry, I'm sorry. What?
Post?
No, keep going. It's God, I'm just drawing a blank. I'm so sorry. I bet it'll come to me.
Southern Panhandle, Caprock.
Off the Caprock.
Off the Caprock. Gotcha.
Off the Caprock, yeah. Scurry County. Scurry County. Sorry about that. I know what it is. I spent a lot of time there, but I'm just drawing a blank. Now, in all of this time, all of these projects, all of this, there's not been leakage. There's not been an environmental impact. There's not been any bad thing happening at these projects. So how do we know what would happen if it did leak? Like, they don't leak, but I'm a scientist. I need to research this. I need to understand what would happen, right? So the only way to know what would happen if one leaks is to make a leak on purpose. And so that is our main approach to studying how we're going to monitor and what the impacts would be. There's been several of these around the world. The first one is called the ZERT, controlled release. And in this project, this was in Montana, you see a pipe that is very shallow. It's buried very shallow in a shallow aquifer. And then CO2 was on purpose bubbled into the aquifer and allowed to release. And then scientists from all around the world came and studied the environmental impacts and studied how they would monitor it and what their techniques could do. And so that's one example from about 20 of these projects that have happened around the world. We've also had them in the offshore because we also can store CO2 in the rocks way below the seafloor. These have been in the UK. This one was Quicks in Scotland. That was in shallow water. And then we had a deeper one in the North Sea. So this is the way that we determine what environmental impacts would be. And in fact, so what is the big deal? What are we concerned about? Well, if you put CO2 in water, you get Perrier. So, you know, what's the big deal about that? No problem there, but that wasn't what we were concerned about. We were concerned about carbon dioxide lowering the pH of the water and then mobilizing heavy metals into the aquifer, because when you decrease the pH, you get mineral dissolution that can then, when the minerals dissolve, there's heavy metals inside the lattice or attached on the surface, and these could be released. And so this was something we had to look into. The other thing we didn't want to happen was brine being pushed up, because brine is salty water. And if you have salty water, you can't drink it. So that's another issue that we don't want to happen to the groundwater. So we put every scientific approach that we could to this problem. We use laboratory experiments, and this is a photo of actual aquifer material in beakers with CO2 being bubbled through. And then we do the analysis on the water to see what metals are mobilized. We looked at this with shallow controlled releases. We also looked at this at natural analogs, because there are areas where CO2 naturally resides in the subsurface. So we can look at natural analogs, and then we can also use modeling. And what we found, and the same thing from every approach that we used, is that metal mobilization was not a big deal. We were very happy to find this. It's extremely transient. I mean, you can't even really monitor for it, because it drops out so quickly. You might not see it. It self-remediates itself. It drops back. It wants to be in the mineral or attached on the surface. And most of the time, if metals were released, they didn't even rise enough above the drinking water standards. So this was a great, really, really significant outcome coming from different researchers and different approaches. Really, really good. But what about terrestrial impacts if CO2 were to ever reach the surface? Well, what we found is that if you look down here on this lower picture, you kind of see the spatial, footprint of the leakage. It's small. We found also that a lot of plants and microbes, they actually have uptake mechanisms for CO2. And this is another point I want to make. Because carbon dioxide, all right, is a naturally occurring component of the ecosystem. It's everywhere, all right? If you think about other contaminants, which we are horrified by, right, from industry and contaminants that have been put into the environment's never seen those. Those are not normal constituents of the environment. CO2 is. So whereas it's a waste product, it's not really a waste. It's something that we all live with all the time. And so what we've seen is that plants and microbes actually do know how to deal with it. And however, if we do get an impact, it's going to be the plants that do not have well-developed root systems. Those are the ones that are going to be the most impacted. If we had leakage in a marine system, what we would find is we would find bubble plumes of CO2 rising. We'd see CO2 partitioning into the seawater and nitrogen partitioning into the bubble. And then that CO2, and so at one point, that bubble that's coming up is nitrogen. And then once the CO2 is partitioned into the seawater and dissolved into the seawater, well, what do we know? We know that now it becomes less dense. It sinks to the bottom. And so anything that can move that doesn't like it scurries away. It's the immobile bottom-dwelling biota that can't get away that would be impacted. But I've also seen times when fish and sea urchins and crabs kind of like to hang out in the bubble stream. So I don't know why some of them like to do that, but they don't always run away. Sometimes they like it. But it's the larvae or the babies of the calcifying organisms that are especially vulnerable to a leak, okay? So now we have a better picture of the fact that these leaks, if they were to ever happen, would have a relatively small footprint and would be transient. So really, really good outcome for the safety of CO2 storage. So do we have enough space? That's another question I hear people asking. And how much do we have to store? Well, as I said, we need 220 gigatons total by 2070. And we have an estimate, it's funny, we have an estimated about 1,000 to 8,000 gigatons of storage in the subsurface available. But the thing about that is that not all the storage is going to be near the facility. right? So we're going to have transport. So we have enough storage. We know that. But we're going to have to transport that CO2 either by ship or rail or truck or pipeline. But pipelines are another thing that people don't like or don't feel safe about. And so let's talk about CO2 handling in the US. So currently, for enhanced oil recovery, since 1972, we have pipelines. We have CO2 pipelines. We have about 6,000 kilometers of CO2 pipelines. 80% are coming from natural sources. They're actually mining CO2 deposits in the ground. So that's something that's can change. I mean, we're going to be using anthropogenic CO2 that we capture from a facility. And of course, all of this right now, most of it is for CO2 EOR. Now, CO2 EOR does store carbon. It stores carbon, and we know this because oil companies spend a lot of money for that CO2. They inject it down, it brings the oil up along with the CO2. They separate out the CO2, they re-inject it, and then they take the oil and they sell it, right? So why do you need a pipeline? Why do you need a pipeline if you're just going to re-inject the CO2? And the reason for that is because the CO2 doesn't come back out. It stays down there. It wants to be down there. And so they have to actually build pipelines to be supplying the CO2 that is needed now. Of course, the climate benefits are lessened because you're bringing more oil out and you're burning oil. And so you're making more CO2, right? So that's not going to go on. That can't go on forever. That's not going to go on forever because we have to transition away from these fossil fuels. But what CO2 EOR has done is make these demonstration projects a little bit more economical, okay? Because CO2, CCS is a waste disposal technology. It has no economic benefit. And so for now, what CO2 enhanced oil recovery is doing is giving us the experience in CO2 handling and everything that we need to know to start storing it. Now, in order to get to scale, we're going to need 80,000 kilometers of new CO2 pipelines, okay? But just to put that in, and that sounds huge, but just to put it in perspective, we currently have 800,000 kilometers of hazardous liquid and natural gas pipelines, okay? So hazardous liquids that are really toxic and natural gas pipelines which actually explode. Now, CO2, as you know, the hazard with that is that it displaces oxygen and it can asphyxiate you. And so there are dangers, definite dangers to CO2. But to put it in perspective, we already have a lot of pipelines under our feet of other liquids that are just as bad, if not worse. I think they're worse. And we do it. We know how to do pipelines. So pipelines are something that we're going to need. What about the cost? Yes, CCS is expensive. It absolutely is massively expensive. It is a very large scale and complex technology. But the good news is we are moving down the cost curve. Since the Boundary Dam plant was the first large-scale CO2 capture on a coal-fired power plant, and then we had the Petronova project, we are coming down that cost curve. So it's an interesting argument when maybe somebody says, CO2 is so expensive, so we shouldn't do it. But if we do it, then we can't ever make it not expensive, right? So it's like this circular argument. We've got to do it to make it better and to get better and to take it down that cost curve. And I'm reminded of the cost curve of a solar panel. Solar panels started being developed in 1976, some 40 years ago, I guess. And at that point in time, the cost of a solar panel was $106 per watt, okay? And if you look at these lines, each line shows a doubling of the capacity that's installed. So each doubling of the capacity brought the technology down that cost curve. And now we have a solar, we can get a watt from solar for 38 cents. This is great. And I'm really glad that back in the 1970s, we didn't say, oh, well, that's too expensive, forget that. And I'm glad we developed it, right? And really, that's what we need to do for every single mitigation technology we have. We've got to develop it and bring the cost down. And we have innovations. They are ongoing. We have innovations happening all the time in carbon capture and storage. So we are coming down that technology development curve. And so this is how I see it. So at first, a technology sounds like science fiction. Like, why would we ever do that? Like, it sounds crazy. And then as we start doing it, we think, well, okay, we could do it, but it's too expensive. And then as time goes on, we go, well, okay, it makes sense in some circumstances, until finally it's just routine deployment and we're just doing it like no big deal. So I hope that I hope and I believe that CO2 CCS is actually coming down this technology development curve so that we can get to the routine deployment. I'm starting to come to the end here, but just a couple of things to, and I hope I'm okay with time. Okay, I'm coming to the end. So is it expensive? Well, I looked up what the IEA says about it. And what they say is that, the high cost kind of ignores the big picture. And that's where I'm coming from. It's like, if you actually understand what is at stake, then nothing is too expensive. I mean, what would we do to save our biosphere? Like, we'd do anything, right? Because once we lose it, we can't get it back. And we can't survive without it either. So, so for me, whereas I know cost is expensive. I do get that. But the bottom line is we need all hands on deck. And to me, there's nothing too expensive to save our biosphere. Basically, they say that we can't get to where we need to go without CCS. We need it. And for some industries, it's really the cheapest and the only abatement option. And I'm talking about cement, iron, and steel, and things like that. We need it to support renewables. We can do more renewables if we have CCS, because we have that backstop of that dispatchable energy, but without the emissions. And so, but we need the policy, right? We need policy to support it. There's no economic driver for CCS. It's waste disposal. I don't know about you, but I have to pay for a truck to come to my house and take my waste. Sometimes I wish CO2 was purple, because if it was purple, then maybe some people would think, oh, I don't really like that. I'm gonna go ahead and pay for it because I don't like it, but because they can't see it and it's not impacting them right now, they don't think that they don't want to pay for it. So anyway, we need the policy to support. And I know that Bob was talking about that earlier, about how we have the Biden infrastructure law and we have the Inflation Reduction Act, which is really, like I said, is at the scale we need. So that's the policy support that we're needed, and it's working. So here's a quick analog. Y'all were talking about this earlier as well. The acid rain analog, we started to see the damage from acid rain, and we decided to do something about it, basically. And we found that the sulfur dioxide, the SOx and the NOx, and the soot and particulates, exactly what Bruce was talking about earlier, the pollution, what we do? We put policy in place. We said, you can't emit that stuff. We said, you can't do it. And look what's happened. We've actually been able to make a difference, right? We have made a difference. So when you look at the technologies, and this is from a peer-reviewed publication from what they learned at Boundary Dam, when you look at the peer-reviewed publication, you see that how did we do that? We put a scrubber on the stack and we said, you cannot emit sulfur dioxide. And so that's what we did. And when you look at the technology for scrubbing CO2, it's the same thing. And what we're learning, and what we learned from Boundary Dam, which was on a coal-fired power plant, the dirtiest energy you can possibly have, was that in order to capture that CO2, you must take the other pollutants out first. So the beauty of CCS is that it is improving air quality from these stacks, because you can't capture the CO2 until you scrub every other pollutant out. So that is the good news. And with these projects as well, we're looking at diversity, equity, inclusion, and accessibility. We're looking at community benefits. And I think this is really one of the things that can deliver really good benefits, especially to populations living near these plants. Anyway, just a quick couple of sundry little items here. Just talk briefly about removals. Removals are going to be needed because we are not stopping the CO2 emissions fast enough. Now, there's a lot of removals, a lot of different types of removals, but the ones that are being looked at the most rigorously right now, because these are the ones that are actually within the IPCC, a lot of these are not, they're not to the point of being included yet, is the land-based removals, which is afforestation, reforestation, better land management, better agricultural practices, and wetland restoration. And then the deep geological storage, the CCS, on bioenergy and direct air capture. Now, what's interesting is currently we're getting 2 gigatons a year removed from the atmosphere. Great. And the permanence is around 100 years. And the reason for that is because trees die and then they decompose and then their CO2 goes back to the atmosphere. We have forest fires, which are becoming more and more of a problem. And with like land use type removals or agricultural practices, you might have a farmer doing some really good stuff, but then that farmer moves on and it's no longer happening anymore. So the permanence of those removals are about 100 years, and the ecological co-benefits cannot be, they're just beautiful. Of course, we need more forests, we need better soil, we need all of that. So yes, 100 times yes, we need all of that. For the engineered removals with CCS, we currently have 0. It's not happening right now. The technology for direct air capture, where you suck CO2 out of the atmosphere using big fans, is in its infancy of development, okay? But the IPCC believes that we could get to 5 to 40 gigatons a year with this. I say bring that on. I like that a lot. And the permanence is tens of thousands to hundreds of thousands of years, because once it's in there, it's in there. And the air quality benefits are beautiful. So I say yes to both. We need both. And the other thing I wanted to say, what was the other thing I wanted to say about that? The permanence, it'll come to me. Here's the other thing. I hear a lot of people, so I've been at the COPs, right? And I know a lot of people don't like CCS, but there's also a lot of misinformation on CCS. And there's a huge number of people that say it's simply a greenwashing technique. That's all it is, okay? But I think, and I've told the youth this, I think their argument would be a lot better if they would actually do an assessment. Do an assessment. Don't just go around saying they're greenwashing. No, how do you know? Let's put an assessment. So I looked it up, and it's another UN document. I love it. It's a UN appointed expert group. How do we assess greenwashing? And how do we hold fossil fuel companies' feet to the fire to make sure that they're actually doing this and they're not greenwashing? But if they, but maybe not all of them are just automatically, right? So we need to do the assessment. And here it is, and it's beautiful, and it's talking about making sure that these companies have ambition and that they actually act on their ambition with integrity, and that they have radical transparency, which is what these regulations are setting us up for, and that they demonstrate a commitment. And this is what we ask of them, right? And in fact, perhaps we could, during the transition, stop the emissions, because the Paris Agreement's about emissions. It doesn't care where they're coming from. So just to end, kind of an analog for the transition that we're seeing ourselves in right now, is the one from horse to car. So it looked very similar to what we're going through now. It took 50 years for that transition. And we had the same kind of, people are for the horse and against the car, and it's going to be this and that, and everybody has an opinion. But what happened was many professions just disappeared. There were something like 14,000 businesses for building carriages, and that went to 90. So this was a big deal. And in fact, the price of grain plummeted, and the US Census Bureau actually tagged this transition as one of the main contributing factors to the Great Depression. So this isn't easy. There were a lot of people in the wrong industry at the wrong time. So there were a lot of jobs that were lost, but there were many more that were created. And this is where we are now. And in fact, if you think about it, the capabilities and skills of the oil and gas industry can be directly substituted over for carbon capture and storage. So when fossil fuels are gone, and we need to be capturing the CO2 from cement, iron, steel, all of those other industries, and we need to be removing them, we can take those oil and gas professionals and we can give them jobs doing that. So my reflections. Well, my reflections are, and I think you guys are on board with this, but there's some people that aren't, is that this is an emergency, okay? We can't be nitpicking what we're gonna do, this or that or this or that. We need to support all of these technologies that are already recognized within the UN. We cannot fall prey to biased rhetoric. It is your responsibility to make informed decisions and to think about this and to look to the IPCC and the UNFCCC for the sound science behind this. It's very emotional, I know, but we've got to do this methodically and in a way that's going to work. We got to keep up the pressure towards divestment and transition away from fossil fuels. But that's not going to happen overnight. And let me tell you that fossil fuels don't care if you have CCS on them or not. They're going to do what they do. They're going to do what they do. So what we need to do is we need to make sure, at least while we're transitioning away, we don't have those emissions. The emissions are the urgent matter. We need to involve everyone in the conversation. I mean, there's talk that at the COPs, we should not allow the emitters to be in the COP. That doesn't make sense to me. I think that how can you solve a problem if you exclude the people that are dealing with the problem? We need to do this in the spirit of the Majlis. We need to listen to each other. We need to see each other. And we need to really be, we need to let people have their opinions. And then we need these rapid, far-reaching, unprecedented changes in all aspects of society. We need action along numerous dimensions. So what we need to do is work together and help each other to grow where you're planted. And let's do this thing. Let's work together. So I appreciate your attention. Thank you so much. I'm so honored to be here, and I'm happy to have a discussion. I hope I've left time for that.